I don't have time to talk about it. I recommend this review article where we actually motivate the whole business through these screening mechanisms, motivate both the theories and the tests, and some of the tests. Another possible test is the mass function, which also provides some constraints on gravity. So let me just skip to a slide like this, where so the analog of Reyes et al.'s 10 megaparsec measurement is a measurement of modest-sized cluster-sized halo masses on megaparsec scales. So this is a combination of the same kind of galaxy lensing measurement with the black error bars and dynamical measurements with the red error bars that Anna showed you. And so this is in this regime where a transition is happening, and so the results, the predictions of different modified gravity scenarios depend on the richness here, the mass of the halo, and its environment. So for these kind of tests, you really need to take specific models, do full calculations, and then you can get several 10% deviations. So if these red error bars can improve to 10% level measurements, then this combination, this dynamic range of masses can provide an interesting test. Okay, so it's worth noting that because if you're say a PhD student wondering what's a good way to think about modified gravity and what to work on, that there's almost contradictory things that are more or less true. So lambda is the simplest explanation for the accelerating universe. No, it isn't, because gravity being exactly GR is very unlikely in any string-like scenario. So we might as well hope that it's modified significantly and that we don't have it in lambda. Both statements true. Model-independent tests of gravity are what we want. After all, we don't know anything about the theory. But on the other hand, the models that we do have suggest that some very specific calculations will give us some idea on where to do the tests. So we don't want to be guided too much by theory, but we wouldn't be testing gravity but for theoretical motivations anyway. So in fact, we will be guided by theory as well. The best tests work on the large scales. Well, that's true, but on the other hand, as I said, the environments of halos are possibly the most discriminating for some particular models. And finally, something that's true of, that's been true of lensing in general, that we are all involved in some way or the other in these massive, expensive, organizationally tedious surveys, because we want to go after these fundamental questions. But on the other hand, the history of the field is that hardworking individuals who get lucky once in a while provide us with some of the most interesting test physics. So I'll leave you with that. The only fact on this slide is that our universe is accelerating. Thank you.
So I kind of wanted to ask about some of these issues you put up on the last slide, and particularly the question about your opinion of the way forward in trying to get a breakthrough here. Because you can either go down trying to test GR and say you may parameterize things with some parameters, but one of the things that Tom Kitchen was advocating is that we actually want as many theories as possible, reasonably well motivated physically theories to counteract your protest against the theories. But get as many as possible, and then of course we'll have, if we get some even way of comparing them, the evidence in a way of putting them on a uniform basis. But then you get some level of what's the distribution of your theories, and we hope one will pop up to give us guidance about where to go. I just want to know what your take on it is.
I mean, in principle, I agree with you. The problem is that theories are very difficult to construct. There's a couple of models that people have worked out. They're both more or less proved out in an interesting version of the two models. So, I mean, we're hard pressed to come up with a single viable model that you can calculate things with. So, in the absence of such a well-developed theories, I think we do need to work with these effective variables, the effective and ratio potentials, which is a great way to go on large scales. It's just that on small scales, you may be missing signatures that hopefully more theories will come along and tell us. But these screening mechanisms are worth studying because you may be, there's only 2 or 3 screening mechanisms. And so you may be able to distinguish the screening mechanisms, and it's quite possible that a whole set of theories will follow one or the other often.
We have a question in the back, Roger.
Could you say a little bit more about what constraints, if any, the existence of black holes and neutron stars and their observed properties might have on modified gravity theories?
I don't know of any strong constraints that these kind of cosmologically motivated modified gravity theories get from black holes and neutron stars. There was some debate about FR theories and whether there's an instability inside the super high density environments of neutron stars. And so the question was how the screening mechanism operates in those environments. And most people seem to think, I haven't read this literature, that they don't pose a problem for this, the classic FR theories that have a successful commuting mechanism that does the transition. So I don't know a lot beyond that.
So in terms of clusters, I was just wondering if you know, I mean, you know yourself measuring velocity dispersion is really hard. Is there any hope to get those errors down enough to constrain anything? And wouldn't it be better to go with central velocity dispersion of, say, BCG, something like slacks, but then on a cluster scales? Would that help?
Right. These are good open questions. I don't have anything particularly interesting to say. We are trying to do a kind of stacked measurement of velocity dispersion, if you like, on variable scales. And the data look kind of simple. They're described by a combination of Gaussians, but if you stack enough, anything could be described by a combination. So it's a little hard to say. Certainly, looking at in the inner regions it seems very appealing. Of course, if you ask real modified gravity theorists, they have strong opinions on where you should test. But I think we should take them with a grain of salt because they're influenced by the particular screening mechanism of their theory. So in some cases, we might say that all these scales you're all of a sudden to be the theory, but we don't really know. There's not.
One last question.
So in the work that we were doing with Razor's help, we had to make a lot of corrections for systematic errors due to nonlinear evolution and bias and so on. For modified gravity theories, there is very little simulation work where you're actually making these corrections at the accuracy that you need. So I think there's obviously, the linear theory gets us so far, but we really need to push into doing the simulations of a set of modified gravity theories that could be representative. And that's going to be the challenge for the theorists, I think, to produce something where we can have maybe this eta approach can be simulated. But if you want to, like Andy was saying, have a huge space of modified gravity models, this is going to be pretty challenging for numerical theorists to get anywhere.
Yeah, that's a great point. We really need a lot of careful simulations. They're interesting sense for how this screening mechanism and complexity occurs inside halos. There's a nice paper by Fabian Schmidt earlier this year. A simple description that captures a lot of the reasons. Thank you.
Thanks for that again.